morning, everyone. Welcome to the second day of Hack in the Box Security Conference 2012 Malaysia. Our next speaker is Stefano Zanero, Assistant Professor, Politecnico di Milano.
That was awesome. Thank you very much, and good morning. It's very early, so I will try my best not to be too boring. If I see you nodding off, I will try to stop and wake you up in some way. My name is Stefano. I work at Politecnico di Milano, which is Milan's University of Technology. We have 38,000 students working in all branches of computer and non-computer engineering. My talk today is about how do we analyze automatically malware. And if someone has seen the presentation yesterday of the threat grid system that was delivered, this is pretty much complementary to what has been shown yesterday. So you can compare the two talks and find connections. So I'd like to start with the usual boring quotation from Sun Tzu, which serves only to score a point. And the point is that in the battle against malware, there's a significant problem of knowledge. And the problem of knowledge can be easily summarized like this. Malware has been at the root of several security problems since a number of years. You can find Mikko Iponen's talk on TED that tells you the history of the battle against malware. But there's been a significant change that I would like to focus on. And this significant change is that while in the 90s, malware was about the explosive diffusion of self-replicating code, so code that was always similar to itself, in the 2010s, malware is about the stealthy and slow diffusion of code that does not actually self-replicate in most cases. It's just delivered by drive-by installation, and which is always different. Or it has many, many different variations because people keep updating it. And this changes the nature of the problem dramatically because the solution that we have to this problem, the made-up solution that we have to this problem, is actually listing the known malicious files, which is a very good approach if you're dealing with a lot of copies of the same thing, or a reasonably good approach if you're dealing with a lot of copies of the same thing. But it's a very bad approach if you are dealing with different things. Because then what you obtain is something like this. This is the live statistics from VirusTotal for the last week about the detection ratio of antiviruses. So each of these columns is a commercial antivirus. And the orange ratio is actually the one that you want to look at, which is the detection rate for samples that are very likely to be malicious, because several other antiviruses tag them as malicious. And as you can see, even the best antiviruses that you can see, I censored the name so that I avoided lawsuits and protected the culprit. But as you can see, even the best antiviruses do never ever get over 90% of detection rate. And if you are looking at the blue lines, which instead are the detection rate for samples that have been tagged as malicious by at least one antivirus. So these are slightly less reliable because there could be false positives in them, but they are the freshest samples as well. The detection rate goes even lower. That's because our approach to fighting malware is basically not the right approach anymore. And this is a nice picture that I found. It's pretty famous. It's been designed by Icarus, which is an Austrian antivirus company, and it represents the antivirus industry in 1998 and in 2008. And that's pretty much reflects the reality. So one of the issues here is the analyst issue, the knowledge issue, as I started claiming. Because analysts are way too few, and the code to analyze is way too much. So we need better ways, always improved ways, to automatically analyze the code that we have in front of us, automatically reverse engineer malware, and as most of you probably know, automatically reverse engineering something is a very, very difficult problem. So in general, it is so difficult that it cannot be solved, generally and for all computer programs. But it can be solved for some specific subset of interest. And another subset of interest is automatically classify malware, so that we already know when we have a new specimen coming in, at least generally what it looks like, so that we already know what are the difference and what are the things that we are looking for. So for doing both these things, there's in general two different approaches, which are not the right one and the wrong one. They just have symmetric advantages and disadvantages. So static approaches mean you take up your code, you decompile it, you reverse engineer it in some way, you have someone study it, and the benefit is, of course, that as long as you can study it completely, you can understand anything that this code does. The negative part is that, well, you need analysts, a lot of them. You have the difficulty of understanding the semantics, understanding what the assembly code actually does for software that has been actually written in order to be difficult to decompile in many cases. And you have the usage of all the techniques of obfuscation and packing that can be used to hide malicious code and to make it more difficult to automatically or manually analyze it. So what we resort to do many times is just a dynamic approach. I pick up the code, put it in a sandbox. If it wants to run, it needs to unpack itself, and it needs to actually do what it's supposed to do. So I look at the behavior of the code while it actually acts. The problem here is the problem that we called the problem of the dormant code. Because in many types of malware, in particular malware that has a command and control infrastructure, not all the functions are active at all the time. So you may very well have a piece of malware that has some stealthy components that actually unpack themselves and activate themselves only on specific conditions. So our approach in this was basically what Sinsu would have advised us to do, to try to turn this weakness that we have into a strength. And the weakness is malware authors are producing many, many variations of the same malware. So leveraging this weakness means that we use that against them. We try to track code reuse across malware samples and use that to discover interesting features of malware that has not been shown during dynamic analysis. Also, by using variations of the same technique, we can also do another interesting thing that I will show along the end of my talk, to study the actual evolution of malware. So what actually the malware authors are modifying in their code. This is obviously a difficult problem because we don't have source code of malware in most cases. In many cases, we do, because many malware creation kits have source code, and through intelligence efforts, we are able to get them from the bad guys' circles. But the specific source code of most specimens we don't have, of course. Otherwise, we wouldn't have the problem. So our approach needs to start not from the actual source code, but from the compiled versions. And so we created this tool that is called Reanimator in loving memory of the authors of the Cthulhu cycles. You will find this name quoted in the Cthulhu cycles many times. And basically, Reanimator does run malware samples in a sandbox, detect malicious behaviors that we are interested in tracking. Then it can identify the code which is responsible for this malicious behavior. And we call the behavior phenotype and the code genotype in analogy with what happens in biology. It's not really a very good analogy, actually. After much reflection, I find that it has its limits. But then we match basically the genotype models, so the models in the code, against other malicious software that we have in our collection. And we can find malicious software that has not exhibited that same behavior, but has the same behavior implemented with similar, if not the same, code. So the idea goes like this. I have a malware sample. I execute it. It shows a number of behaviors. Most of these behaviors I will probably be interested into, so I track these behaviors to the actual portions of the code that execute them. And I find a reliable model for finding these functionalities across the database of samples that I have. So it does not only need to be reliable, but it also needs to be very fast, because, of course, databases of samples are growing larger and larger. So let's start with behavior identification. To do that, we use an instrumented sandbox that many of you may be familiar with. It's called Anubis. You can access it on the web, anubis.iseclab.org. You go there, you upload a sample or whatever file you want to check. Anubis will run it in a monitored environment and give you a report of what this malware does. So we modified Anubis to have a set of rules to detect some behaviors that we were interested into, and to map, basically, each single behavior to a set of system calls, or API calls, better, which are responsible for it. At this point, when we run our sample shows the behavior that we are interested into. We have a set of calls that the sample does that implement this behavior. So this is an example of several behaviors that we have identified. This is the type of things that we have that we need to write a rule for. So very generic descriptions of things that we may be interested into. So the extraction of the genotype is actually the specifically difficult portion of this work. Because we need a complete genotype, so as much as possible of the code implementing the behavior, and a precise genotype. So a way to match that code that does not match against code that is not specific to that behavior, because otherwise we would generate false positives. So we proceed by 3 steps: slicing, filtering, and germination, and I will explain each one of them. So the first step is called slicing. We basically start from the calls that we identified as implementing the behavior. We include in our slice of code any assembly instructions that either prepare input for those API calls, so we follow the data dependency backwards from call inputs, track backwards what is preparing that call input, or instructions that process the output of the call. So it's the classic taint flow analysis of input and output of these calls. We do not consider control flow level dependencies. This is a limitation of the approach, but it's necessary because otherwise we would have the taint explosion. So we basically would include everything in our analysis. So this slice obviously is not precise, at least because it includes code that belongs to each utility function. So the bad guy maybe wrote his own function to reorder bytes in whatever data structures they are using. This function gets called, and I will see this function included in my slice. But then again, if they call it throughout all of the code of their malware, when I run a search, if I include this in my slice, what will happen is that I will have a lot of false positives because I will find that there are thousands and thousands of functions in the malware that are actually matching. Or functions that come from libc, from standard share libraries. I want to get those out. The second thing is that backward slicing is just too much backward for us. So it goes back, and at some point, it will end up including initialization. And if it includes also the unpacking routines, then we are screwed, because we will match anything that has been packed with the same packer. So what we do basically is filter out the instructions that are not really exclusive, which means filter out the instructions that, so the exclusive instructions that are the ones that we are interested into is the instructions that basically every time they are executed, they only work on tainted data. So we exclude instructions that can possibly be called on non-tainted data. This obviously takes out all of the utility functions, or at least most of them. The second way for filtering is basically if I execute the sample multiple times and it doesn't show the behavior that I'm interested into every time, I take up one execution that has not shown that behavior. I look into all the instructions that have been executed in that execution, and I filter those out, because those are evidently the baseline of the execution that does not have anything to do with my code. At this point, since I've been filtering and filtering and filtering, my slice is obviously incomplete. I'm left with only the instructions that are exclusive to the behavior, but this is not sufficient to actually have a set of instructions that will run. So what we do is we pick up these instructions and we basically complete the graph by adding all the instructions that cannot be executed without tripping on at least one of these instructions. In this way, basically, we are reconstructing the reachability of the control flow graph of these instructions. So what we end up with is the set of instructions that implement the behavior in a completed version of the control, or a sub-control graph of the program. At this point, what we need is a way to match this portion of the control flow graph against a huge database of other malware without running into a problem of performances. So since basically the genotype is a set of instructions, it's a sub-piece of the control flow graph of the malware, we model it by using its control flow graph colored with the type of instructions that is contained in each single basic block. So we basically divide the x86 instructions into categories, 14 of them, and according to the presence or absence of these categories of instructions, we color the block based on these instruction classes. This model was originally proposed by Christopher Krugel a few years back in order to analyze, in order to analyze polymorphic worm code. And basically, the idea is that you build this graph, you color it according to the instructions that are present in the basic blocks, and then you build subgraphs of size k. In our exercise, we used size 10, which is a reasonable compromise and trade-off between precision and speed. But people may wish to change this to suit their needs. And in this case, what you do is basically you build all of the subgraphs of dimension 10, and you look throughout your database to see if there is a malware that has the same subgraph inside its counterflow graph. So this may sound very expensive, but actually, since most of this thing can be done once per each malware sample, so you can store the malware sample along with its size 10 or size whatever you want fingerprints of subgraphs. You can do this once for each malware, and then you can just look throughout the database, and it's just a problem of matching. As long as your database indexing technique is efficient, this will get you easily the results. So what happens is that the final result of this is that you run a sample, observe a behavior, figure out what code is supporting this behavior, match this code through these graph techniques across the database, and you end up with hundreds of other samples that match that subgraph. So then the question is all of this that I have proposed is very reasonable, but does it actually work? So are the results accurate? And this means basically two things. First, if when Reanimator detects a match, there's actually code that matches that. And second, how resistant is this matching to techniques that malware authors use to try to obfuscate their code? And there's a third point, how useful this turns out to be. So to test accuracy, obviously, we needed a ground truth. So we got a data set of 208 boats with source code. This came from a data set that the University of Michigan is using. From one of these bots, we extracted 6 models of 6 different behaviors, just to test. And we matched these models against the compiled versions of the remaining 207 bots. Then, of course, manually verifying code similarity would have been very time-consuming. So what we did was we took a shortcut. We used MOS, which is a well-known plagiarism detection tool. If you have been through university recently, or if you are a university teacher, if you're a university instructor, this is cool. You can check code for plagiarism among your student submissions. So basically, we fed MOS with the source code corresponding to each of the 6 behaviors, and we matched it against the other 207 bots. And MOS does not tell you, yes, it matches, no, it doesn't. It returns you a code percentage matching. So basically, what we expect is that Reanimator should match on code that has high similarity scores. And this is the comparison. It's a bit tricky to see this graph, so please follow me. Basically, this is on this axis, you have the percentage of matching code according to MOS. So how much of the code matches. And here, you have the number, since I couldn't show you on a slide 208 samples with the results. We have looked at the results one by one. The PhD student who was co-author of this paper looked at the matching instructions. Thanks, Guido. You will not be forgotten. But here I'm summarizing it. So I'm showing you the number of samples that fall in this bin. So there's X number of samples, in this case 240 something, that fall in the 0 to 5% similarity bin. This means that they do not match according to MOS, and we do not expect the Reanimator to show that they match. So basically, if you understood my way of representing data, the difference between this column and this column are the potential false negatives, in this case, of Reanimator. Because MOS says that there's more matching code than a reanimator would say. And this are the potential false positives, because Moss says, yeah, that there's like a 20% match, and a reanimator says, but there's a match of my fingerprint. So, once again, useful PhD students has looked through these things, and basically, so we manually investigated, translates to we do manually investigated the potential false positives and false negatives, and the result is there is a low false negative rate. So in some cases, in particular when the function that has been executed is really small, our approach may fail. It may not identify matching code in another bot. But what's interesting is that this approach shows no false positives. So the few false positives that you saw that were manually investigated and actually found to be reimplementations of the same behavior that for some reason fool Moss. So the false is on Moss side and not on reanimator side. And this is interesting because we also ran checks on a very large database of fingerprints for behaviors on over 2,000 binaries that come from a clean install of Windows, and we found no matches, which could be seen as a negative result because many people would like Windows to match against a tool that checks for malicious code. But still, this was the expected result. So we checked if this would be robust when compiling with different obfuscation tricks and techniques. So it was robust against compilation options and different techniques that can be used to change the actual compiled code. But it resulted not to be robust against completely different compiler. This is explained because different compilers have different calling conventions, and this can cause differences in some parts of the graphs. We are working to see if there is any fundamental issue with this, or if it's just an issue of, again, of matching that is present in our current version of the code, because there's no theoretical reason why this should happen. So I attribute this to a limit of our present tool, not of the technique itself. Then the other question was, how much does this work if we try to figure out what behaviors are in the wild? And we used 4 different data sets with thousands of samples. And basically what happens is that for some data sets, there are impressive results. So there's just maybe 50 or just 1 sample that executes some behavior during dynamic analysis. But then, if you actually run a reanimator in it, you find that there's over 200 samples that have that behavior implemented and did not execute it. So at the end of the day, the detection by a reanimator turns out to be a useful tool to find code that has been left dormant in versions of malware. Very precise. There's no false positives. It may have false negatives, but false negatives are better than nothing, right? And it is reasonably resilient against obfuscation techniques. The one limit of Reanimator that we will put forward is the fact that it works on unpacked code. So you need to unpack your malware first. That's a problem that has different solutions. So then, we studied a slightly different take on this problem. So the problem of tracking malware evolution over time. As we all know, one of the reasons why the malware problem is so difficult to solve is that, as I said at the beginning of my talk, malware authors are constantly updating their code. And so we wondered, 1, how much are they constantly updating this code? 2, how much of these updates are done with the specific intent of, changing something to avoid detection, but not really changing the functionality, and how much of these updates are actually changing the functionalities? And three, what is the actual level of development effort that goes into this? So is it just the small changes, like small edits, or is it structural, interesting changes? So we created a prototype, which we called Beagle, like the dog. And basically what Beagle does is get a set of malware, get a data set, let this malware update itself. So every day we let it connect back to its command and control server, receive any notification of changes, and update itself. And then let it run into monitored environments so that we can see behaviors. Every time it updates itself, we also track back these behaviors to the code, and we monitor changes to the malicious code. So basically, this tracking back and identifying uses the very same techniques that I just illustrated for Reanimator. So the interesting part is how do we actually analyze and semantically understand the difference between code. So this is a schematic that represents what I already said. Basically, I have my sample. The sample connects to the update server, and over time, it changes in versions. Every time a version changes, I execute it into a dynamic analysis environment. I log its system-level activity, and I analyze it from the binary point of view, an unpacked version of it once again. Same basic requirement as a Reanimator. It needs to unpack itself. And we basically run a binary comparison between the different versions and a comparison of the difference in behavior. And we try to put these two things together semantically. So the definition of behavior is actually very similar to the behavior signature of Reanimator. We don't use Anubis in this case. We use an Anubis-like sandbox. It was more efficient to do this. And we analyze system-level activities. Basically, while in Reanimator, we were focusing on one single behavior, and we were trying to discard all the code that was not related to that behavior. What we do in this case is we focus on executions of different system calls, and we call this unlabeled behaviors. It's something, because they have been executed together, they have been acting on the same values, they have been acting on same variables, so they are probably an aggregate that does something, but we do not know outright what this thing is doing. So basically, these unlabeled behaviors are clustered of system activity that may be interesting. Then, an analyst, namely us in this case, looks through this behavior and manually labels them, some of them at least, saying this is an interesting behavior and this is the bot doing spamming. This is an interesting behavior and this is the bot connecting to a command and control infrastructure. We can generate some rules and recognize these behaviors across different samples, pretty much in line with what we were doing with Reanimator, but basically we are doing it the other way around. So in Reanimator, we were doing this top-down. We were defining a rule and then matching it. In this case, we are looking at the aggregates, and for some of them saying, OK, this is interesting, and I write a rule for this, and I match it across the other samples. Also, while on Reanimator, we used a basic block level aggregation, basically. In the case of Beagle, we decided for function level granularity. So when we include a piece of a function, we decide that the whole function is interesting, because we are trying to track the evolution of code over time. We are not really interested in matching code across different samples, so we may be interested in sub-pieces of code that maybe have been rearranged differently. Here, what we are looking for are actually small changes in an infrastructure that is already built. So this is the data set, which is, I realize, a little bit small, but you will get the slides right after the talk, so you can. So this is actually a reference for you when you get them. And it actually includes several well-known malware families. Zeus, Kelihos, and Gamaru are some typical names that you have. If you have ever worked with malware, you know already them. Oh, basically, while I'm at it, actually, it's called Zeus, not Zeus. Zeus is American version of the pronunciation. So, just for putting it out somewhere. But still, we are working on American English, so we say Zeus all the same. So these are some of the results of Beagle. Once again, I don't really want you to try to look at this. You will look at it on the slides more comfortably after the presentation. But basically, what we get out of this as insights is this. On many of these families, there's an average. These figures are the average percentages of added, removed, and shared codes between two subsequent versions. So on some of these families, on many of them actually, there's a consistent percentage of 5 to 10% of added code between each version. In this case, added code is computed in terms of basic blocks because we cannot really know the lines of code that implement the assembly. But still, it's a measurement. Overall, malicious guys are really actively adding, subtracting, and changing things across versions. They are not just edited to try to change slightly the malware not to fit a signature, but they are actually actively implementing some changes. So another interesting thing that we can do is break down the changes across a single malware family according to behaviors. So here I have several different behaviors: download, execute, change the security policy of the host, generate UDP traffic, spam, that are all executed by samples of the Gamaru family. Across the different samples, this is basically the distribution of the similarity between one sample and the previous sample. So what the median means is that if the median is a similarity of 1, it means that those functions are not really changing much. So for instance, the function DNS query, unsurprisingly, does not really change much across versions. But then, in some samples that are marked with this small ball over here, in some samples, it happens that one of the changes is an outlier. So UDP traffic, DNS query does not change across basically all of the version. Then there's one version where the difference is complete. And this is very interesting because it pinpoints one dramatic change. Well, in the case of DNS query, maybe not so dramatic, but one dramatic change that the malware others have made. So I know that if my function varies always little, and then there's one sample where it varies a lot, that's an interesting sample to look at. And I don't need to look at the whole sample, necessarily. I just need to look at the specific function, because that's where the interesting change has been. Functions that the boxes are the classic quantile representation. I will not go into it. If you know about quantile representations, then it's clear. If not, basically, the size of that box indicates the variance of the change across the different versions. So where there's a large box, it means that that specific piece of code can be very similar or can be very dissimilar. It fluctuates. And this is interesting because the ones where you see all these possible variations, or even where you see a median which is very low, a median of similarity which is very low, means that the guys are constantly changing that specific piece of code. So it means that those are the functionalities that in the gamma rho family are either more used or more interesting because a lot of development effort goes into them. Or they are the functionalities that correspond to the anti-malware signatures for that family, so they keep changing. These are some of the other insights. Actually, all of the results of this study will come up at a scientific conference, which is called ACSAC, at the end of the year. But if you want to have a previous release copy of the paper, just ask me, as long as you don't distribute it before December, as I will be presenting this also at Hackers to Hackers conference, the conference run by Rodrigo. I will share it with you. Just don't repost it on the web. So this is a summary of the insights in the paper. Basically, some families are actually much more actively developed than others. So there's some families that are basically mature. They're just sitting there and doing their stuff. And there's other families that keep being changed. Thanks to Beagle, we can pinpoint changes over individual behaviors and sometimes run this across the collection. So we can put this on a graph and basically look at it and see that in some specific days, not only some behavior has been changed in a specific family, say Zeus, but maybe there's a matching change also in Helios or in other families. So when this happens, we know that there's some subterranean activity, some underground activity that is forcing different malware authors or different groups of malware authors to change the code at the same time. There's probably something interesting to look into there. In some cases, for some families, what happens is that if you look at the global numbers, they seem relatively stable. They change little. But then you disaggregate that for behaviors, and you see that a number of behaviors are stable. And then there's one that is constantly changing. So you know that the malware family is actually still under active development. They are only focusing on one single piece of it, either because it's the one that they still don't get right, or either because it's the one that they are more interested into at the moment. But it may look like, superficially, if you just look at the complete set of code, it may look like they are very, very similar to each other. But actually, there's a specific behavior that is changing. Finally, what we wanted to do was to try to make this an evaluation of the development effort that goes into this things. So here the challenge is that we have blocks in assembly and not lines of code in source code, which is the usual metric for development effort that software engineers use. But we can do some estimate and go backwards from there to the line of code, to the lines of code implementing those changes. And we estimate that the average added code in Zeus over each variation, so over each different subsequent version, is about 140 to 280, let's say a couple of hundred lines of code, which is not terribly much, but it's actually a significant, consistent, continuous development effort. And what happens is that in some versions where there's a dramatic change in the functions, this ramps up to 9,000 estimated line of code change, which over a bot, which is not a very complex software, means a significant redesign effort. So there's actually significant effort invested in updating these things. And this basically roughly holds the same for other families. We are less certain because in the case of Zeus, we have the advantage of having some of the source code for some of the versions, so we can map very well back to the number of lines of code implementing that assembly. I'd like to conclude my talk with the presentation of a future issue that we are going to address, which is the issue of malware classification into family. Basically, this is an open problem with much confusion. And classifications given out by antivirus vendors are completely unreliable. which is not a bash against vendors. It's just that it's not what they are looking for. They are looking for having some of that classification internally, but as far as the signature names that they put out for us to see, they don't really care, right? If you call it a rose or if you call it a violet, but it's actually still matching malware, they are fine with it. We basically demonstrated this. We picked up a large data set of malware, ran 4 commercial antiviruses on it. That representation at the right is basically one of the representations that you can find into the paper. It's a paper on malware inconsistencies. You will find it in the list of my scientific papers. It's for 1.5 years back. But even just not knowing how these graphs have been obtained, but just looking at them, that's the classification done by the 4 antiviruses of the same data set of malware. Even just looking at them, you can spot the fact that not only they are different, but they are completely unmappable to each other. They have structural differences that are so great that there's no way to match them to each other. And this is important because normally when we think about inconsistencies in naming, what we think is that, well, yes, there's some weak inconsistencies, right? Some antivirus company may call this Zeus.A and then that Zeus.B, and the other anti-malware company calls both Zeus.C. But if you map those, you will be fine. Actually, it turns out not to be the case. Turns out that you cannot really define a mapping that brings one of these taxonomies to the other, which means that they are completely fucked up. So one of the things that we would very much like to do is to try to, we as scientists, would like to try to figure out a way, a better way, of classifying these things. Because this way is just not strongly founded. It's just based on the best approximation that a malware analyst wants to do. So there are several works in this area. Many of them work structurally, so they work based on static analysis of code features. Halvar Flake and Eero Carrera come to mind. Others work on the behavior, on the dynamics. And their works by Paolo Milani Comparetti and Christopher Krugel come to mind. But the idea is, okay, so we have seen that combining structural and dynamic features, you can actually get better results at identifying the behaviors. So why not trying combining those 2 things also for the classification of malware? Or this, let's say, not classification, because maybe that's too much to ask for, but at least a clustering in significant families. And this is what we are currently trying to work on. So my conclusions for this talk, in perfect timing, whoever said that Italians are not punctual, French do not count. Structural analysis alone is too time and brain consuming for people to do across all of the malware samples that we have. Dynamic analysis alone can be automatized, but it misses many points. So we can combine both to obtain the analysis and tagging of dormant code that has not been observed in behavior in dynamic analysis, to track the evolution of code over subsequent version, to perform an efficient triage of new samples, both by looking for known behaviors in them when we receive them, or if they are a new version of a known malware family, to see where the significant changes have taken place, if a significant change has taken place also. And hopefully in the future, it will give us a better means of classifying specimens in families or in clusters of relevant interest. There's much work that needs to be done in this area, which means that I will have a job for the next few years. I thank you for your attention, in particular for being up so early for me. My email address is stefano.zanero@polyme.it. I'm very open to receiving feedback and questions. If you want a copy of one or both or whatever papers that are connected to this, please feel free to write me. I will be very happy to share that with you. I would just like, before taking questions, I would just like to mention that many of this work is not just my work. It's work that has been done with Christopher Krugel at USCSB, Paolo Milani Comparetti working at lastline.com, which is a startup in California, Engin Kirda, professor at Northeastern University, Martina Lindorfer, Federico Maggi, and Alessandro Di Federico, who are students of Technical University of Vienna and Politecnico di Milano, who were the ones that actually did this work. Of course, they are co-authors, but errors and opinions are just mine solely. So thank you very much for your attention, and if there are any questions, I'm happy to take them. Any questions? Yes, sir. Is there a microphone, maybe, so that the audience can hear? It's over there.
Hello. I want to know your opinion on the context-triggered piecewise hash (CTPH) method for calculating distance between malware variances. For example, the deficiency of using MD5 hash sum is that if you're comparing two different variants, the MD5 totally will be different. But by using SSDIP, for example, which is the application that using the CTPH method, the distance might be not, the hash that being produced will show some kind of similarity between two variances. Did you ever came across that method? And if you did, what is your opinion and what can be improved for variance comparison or malware family class?
Okay.
Yeah.
So if I get your question correctly, basically what you're asking is what are the techniques that we can use to analyze the similarity or dissimilarity across different malware samples, their affinities and their similarities? Is that what you were asking for, more or less?
Whether they came from the same family. Let's say you said Zeus A, B, C.
Mm-hmm.
So let's say they have inherit the code. Let's say A, B, and C inherit the code from A. How can we actually show that? So
yes, that's actually something that has been more than related to my own work. That's something that you will find in the works by Halvar, Flake, and Bayero. They basically used several models on the call graph structure of malware to see if there was any significant heritage from one type of specimen to another. We didn't really do that work, but the basic challenge in doing that is that, and you can actually do that with the technique we have used, and you will probably reach the similar results. The actual challenge in doing that is that nowadays, while once you had a very tree-like structure of derivation, you had an ancient sample, then you would have different evolutions of that sample, and it would basically disperse itself across different variations. What happens today is that actually samples inherit from multiple ancestors, so it becomes difficult to say what is the father and what is the son between two samples that share some pieces of code. So our approach was more oriented to say, okay, I don't know which of the two inherited from the other, but I know that these two samples have a similar behavior, and that similar behavior is actually also implemented in the very same way. So they may have exchanged code, one of the two may have stolen code from each other, or they may just, it may just be that behavior can be implemented only in that specific way. There are some very simple things that, if you put 20 students in front of them and you have them implement it, more or less you will end up with reasonably similar code. as long as something is very simple. So it's very difficult to actually say if there is a descendant tree in that sense. Any other questions? Thank you very much for your patience and attendance to the talk. And if you want to talk to me, I will be around for the whole rest of the conference, so feel free to stop me and talk. Thank you very much.